Okay, here's the package. Applied Research and Technology, ART, Phantom 2 Pro, 2-channel 48 volt phantom power supply. Phantom 2 Pro is designed to do one thing and do it well. It provides clean, reliable phantom power for one or two condenser microphones in a rugged, compact, and portable unit. Innovative low-power circuitry generates the higher voltage necessary for powering microphones while maximizing battery life. The Phantom 2 Pro installs in line between your microphone and a balanced line input on your gear. Balanced lines offer increased immunity to external electrical noise such as hum. Blah 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 blah. The Phantom 2 Pro is an invaluable tool in application areas including but not limited to home or professional recording studios, live sound, PA, permanent installs, DJ, AV, podcasting, and broadcasting. Use it with mixers, audio processors, digital audio workstations, or anywhere you need phantom power for your mics. XLR connectors for balanced inputs and outputs, low power, high efficiency CMOS circuitry for long battery life using a standard 9-volt battery, alkaline recommended. It can be powered with an external power supply for operation from AC mains. Rugged extruded aluminum case with easily accessible battery compartment, LED lighted on-off switch, low noise, low distortion circuitry. Well, yeah, as a phantom supply adder, it shouldn't do anything to the audio signal itself. So that's like one of those freebie kind of specifications. Here's the item, and I already have the battery cover removed. It's an aluminum plate with a little tab that locks into that slot, and then a captive screw that goes in there, and it's just held in place by like a cardboard sleeve. There are the two outputs which do not have phantom power on them, and those go into your amplifier, mixer, whatever. And then here are the two connectors where the cables to the microphones are, and these connectors do have phantom power on them, assuming that you have the button turned on. It's a push on, push off, and it's supposed to be illuminated as well when it's on. And it can be powered from a 9-volt battery, or it can be powered from a fairly generously specified AC or DC power source between 7.5 and 12 volts. So pretty much any, well, not any. If you put in a 5-volt power supply, it probably won't work, but and it's supposed to be diode protected so that, you know, if you hook up the wrong polarity, it doesn't hurt anything. If you have both a power source here and a battery, they don't compete with each other. So I'm going to pop this open. There it is, slid out of its case. It's just a simple extruded case with rubber bumpers on the ends and also to make feet on the bottom. It's necessary to take off all the screws for the XLR connectors and the two that go into the extruded case, I think on one end or the other. I did it on the front, and that allows the whole thing to slide out the back, where you only need to undo the screw there and the screw there, not the ones going into the XLRs. So I don't expect there's much in this except for power supply conditioning. This is the battery cable plug, and it has a few surface mount parts there. I'll scope those out, but there's some transistors. Looks like 3 transistors, 1 or 2 caps, a couple of diodes, some resistors. There's a diode bridge and 2 diodes, 2 resistors, and a capacitor. So I'm sure that the incoming, since it can be AC or DC, is going through the bridge, and then I suppose that I'm not sure why all those transistors are there on the battery. I have to try to scope that out. And the power switch is just simple push on, push off, but the clear plastic button is also a light pipe, and there's an LED on the circuit board that shines up into the light pipe, and then that illuminates the button. So the let's see, these are the inputs here, and they have the DC blocking capacitors. Interesting, yeah. Here it shows that the blocking capacitors are for the outputs, but the outputs are here. That's interesting. Well, I suppose it just depends where they're, you know, these are tied together and these are tied together with just the capacitors in series with both lines of the balanced line. So even though they're located here, electrically they're probably closer to that side. Just depends how they run the circuit board traces. And I expect that those 4 resistors that are all equal value are the phantom pull-up resistors, or the phantom supply resistors, which are shown right there. The way phantom works is that the microphones don't respond to DC, and an equal amount of DC voltage is applied through equal value resistors to both of the 2 lines of the balanced, or both sides of the balanced line, and then the return is the ground. So that would be the negative or common voltage, and then the V plus would be connected. So you have the same voltage on both of those lines, and because the phantom or the balanced line inherently ignores everything that is common to both lines, a common voltage on both those lines would be completely ignored, which is why it's phantom. So the microphone audio circuitry doesn't even know that DC power is being applied, but the power supply for the microphone can utilize it. That's how that works. So I expect everything else on here, this stuff down here, is going to be some sort of little switching power supply, I suppose, or I don't necessarily see an IC on there. Hope there is an IC. So that might be a switching power supply chip, or it might be 5 volt, or like a simple switcher, little switching power supply chip. That would have 5 pins, and that would match that. So not sure. And that would probably be one of the filter capacitors associated with that, and probably this one too. I'll dig into that a bit more. So here's a little diagram I've made up about how balanced lines work for microphones and similar circuits, and also how phantom power works. Over here we have a typical microphone using some sort of a capsule. This would be most likely a condenser microphone, and it needs amplification because the signal here is so weak. It needs to be amplified before it can be sent down the long microphone cable to the preamplifier or mixer or whatever is receiving the signal. This is the microphone cable. Most microphones use XLR connectors. The pins are numbered 1, 2, and 3. 1 is always connected to 1, 2 is connected to 2, and 3 is connected to 3 from end to end. Typically a twisted pair of wires is used for the conductors on terminals 2 and 3, and then 1 to 1 can be a single conductor, but most often it's actually a shield that surrounds the twisted pair and also makes the connection from 1 to 1. So it functions as both a ground, as a common signal, and as a shield for the signal carrying wires. Now we get back to the microphone itself. So we have the microphone capsule, which turns sound waves into electrical waves. We have an amplifier, and the amplifier drives the primary of a transformer, and the secondary of the transformer is applied across terminals 2 and 3. If you look at it from the perspective of the common signal, the signal on terminal 2, is some sort of a waveform, and the signal on terminal 3, again from the perspective of terminal 1, appears to be a mirror image or the inverse. So when this signal is going up, this signal is going down. When this signal is going down, this signal is going up. And they go up and down proportionally and 180 degrees out of phase with each other. At the receiving end, those signals pass through capacitors, which to AC signals seem as though they're not even there. And then we have what's called a differential amplifier at the end. And it's always looking to see what the difference between the two voltages are when referenced to the circuit ground or common. So it sees this signal going up and this signal going down. It takes the difference between them and amplifies that and sends it out as a regular audio signal. When the signal is relatively high, you get a high signal here. When the signal is sort of in the middle, neither high nor low, you get the same thing here. And when you have a negative going signal here, you'll get a negative going signal here. Well, why is that used instead of just a simple wire going through? Well, because of noise pickup. When you have a long cable, there's always the chance of it picking up electromagnetic interference from magnetic fields and so on that it passes through. If you induce a current into these wires from something that you're going near, electrically noisy equipment, etc., or running near power cables and so on, if you induce a signal into this wire, you'll induce the same signal into this wire. Therefore, instead of being 180 degrees out of phase, both signals that are induced go in the same direction. Therefore, there is no difference between them, and the differential amplifier sees nothing because there is no difference in those signals. Therefore, the noise signal is not amplified or passed through. It's completely canceled out. So that's the essence of a balanced signal used for microphones. What is this all about phantom power? Well, the amplifier that's out here needs to have power from somewhere. A lot of less expensive microphones, non-professional microphones, for example, might just have a battery in them, and that provides the power for this amplifier. And indeed, some professional microphones still have the option to put a battery in them instead of using phantom power. One way or the other, you need to have a power source for this amplifier. In this arrangement, there's this additional connection. These two lines here represent the power to the amplifier. So where does that power come from? Well, it comes from the receiving equipment, whether it's a mixer, a preamplifier, or whatever. there is an additional power supply in this equipment that provides typically 48 volts DC, with the minus side of that power supply connected to circuit common or ground, so it's the same ground shared by the audio signals. And then the positive side is connected to two resistors, 6.8K or 6,800 ohms each, and usually they're fairly precision types that make sure their values are very close to each other. And then those are connected to the two signal lines. So just like noise that might be induced in these wires, and because it's the same amount induced in both wires, it gets canceled out or ignored by this amplifier. The two DC voltages which are applied here and here are also treated as a non-entity by this amplifier and are ignored. Also, it's quite common to put these capacitors here, as I already mentioned, and because this is DC and DC does not go through capacitors, that's another reason why this amplifier does not even see this phantom power being applied to these two wires. But even if the capacitors weren't there, the differential amplifier would see two identical DC signals and would cancel them out. Therefore, they would not be in the final signal. But these two 48 volt DC potentials are passed through the wiring, and at this end, one or the other of them or both make their way to the center tap of the transformer and taken off of it there and sent to the microphone amplifier here. Meanwhile, the minus side of the amplifier gets its power return through the same ground that's used for the audio signal itself. Because it seems like there's no way to get power from here to here without understanding how the circuit works, that's why it's called phantom power. It's like it's invisible means of getting the power there. Or some say it's phantom because this amplifier down here doesn't even see it for the aforementioned reasons. So that's your basic normal setup, but what if you have a microphone here which requires the phantom power, but this preamplifier or mixer or whatever you've got here does not have the phantom power supply in it, does not have these resistors? How do you then power a microphone of this sort? Well, here's another little sketch. Over here is the same kind of microphone that we would have had up here. I just didn't draw it, but we still have the terminals 1, 2, 3. That would be here. We still have the microphone cable going in, but instead of plugging this cable into the final preamplifier or mixer, it goes into an extra piece of equipment, which is an inline phantom supply. And all it does is it adds the circuitry which is missing over here. It has its own 48 volt power supply. The minus side of that is connected to circuit common or ground. You've got the same 6.8K resistors, and they're tied to the same signals going to terminals 2 and 3 of the connector. So as far as the microphone's concerned, you have exactly the same thing as you did in this scenario. And because we're not sure what equipment down here may have, usually capacitors are added here just like they would have been here. If the equipment here also has capacitors, then it doesn't really make any difference. These capacitors are transparent to AC signals, in other words the audio signals, so it's as if they're not even there. So the signals just pass right through. Then you have another cable which goes from this phantom power supply module, and it continues on to the regular input connector for your mic preamp or mixer, and everything from that point is identical. The phantom power works the same way, it's just introduced by this extra piece of equipment in the middle rather than being introduced over here at the input of the audio equipment that you're feeding the signal into. And here's my crummier little sketch. This just represents the specific ART Phantom 2 Pro. It does exactly the same thing as my other sketch. We have the incoming signals, 2 XLR connectors for mic signal 1 and mic signal 2. The signals pass through. There are capacitors in series, 4 of them, and then to the output terminals, which go on through another cable to your mixer, preamplifier, whatever. So just like my other sketch, we have to interject the phantom power, so there has to be a source of approximately 48 volts. There's a filter capacitor, and then there are 6.8K resistors going from that power supply to each of the audio signals for the 2 mic channels. And once again, the capacitors here block any of that from going downstream, but it does go upstream towards the microphone where it's needed. So in that sense, this ART Phantom 2 Pro works exactly like the convention. The only thing that's really different about it is instead of necessarily deriving the 48 volt phantom power from an AC wall outlet through some sort of more elaborate power supply, it's primarily working off of a 9 volt battery and using the solid state booster circuit to bump that lower voltage up to approximately the desired 48 volts. Alright, just for yucks, I have my voltmeter hooked up to one of the terminal 1s. They're all electrically common on all 4 XLR jacks, as they should be, because that is the signal common. And then I have the positive side of the voltmeter connected up to the common of the 4 phantom power pull-up resistors, which in turn I'm basically measuring across this electrolytic capacitor. And that should get charged up to roughly 48 volts whenever I turn the power on. And I'm just powering this off of the 9 volt battery for the moment. I had it turned on a moment ago, and it's slowly, just the resistance of the voltmeter, it's slowly pulling the charge down. If there were any microphones connected, it would pull it down a lot faster. But I'm going to go here and turn the power on. I get the red LED, and the voltage is up here around 46.5, so pretty close to 48. So the power supply for the phantom power seems to be doing its job. If you use the auxiliary power supply here, it seems to come in through a couple of different circuits. One is that it's just connected because this is either an AC or DC power supply, and either side of it, the plus or the minus, which could be either way around, or maybe there is no plus or minus because it's an AC signal. Either way, the 2 pins of this connector end up getting connected to this diode bridge on its AC side, if you will. And the plus terminal here and the minus terminal here, that's the output of the bridge. The minus terminal just goes to circuit ground, which is also common with terminal 1 or the common terminal on all these XLR connectors. The plus side of the bridge comes out and essentially goes right to the power switch. However, both sides of the connector also go to these 2 diodes, which are in turn the anode to the cathode, and then they go through some very small value resistances. I'm not really sure why they're there. That's connected together, and then that feeds over to this transistor circuit, which is on the battery input. And I was having some trouble figuring out from the surface mount device codes exactly what all those parts were, but I thought in general these were either 2N4401 or 2N4403 transistors, all three of them. Well, yeah, I think so. Let's see, 2X, that would be an NPN, and 2T, that would be a PNP. The only one that was really a question was the one marked S5, which might be an NPN transistor, but it might be something else. I really wasn't sure about that one. That would be the one called Q1 here, and that would be the output. I kind of penciled it out here so you can see the barrel connector here. There's a capacitor across it, and then both sides of that go through diodes and then through resistors, and then they come together and it provides a signal coming down to here. Now I measured those at 1 ohm, which seems pointless to me. It may be because some other things in the circuit threw me off, I don't know. But both sides also go to the diode bridge, like I said before. The negative side of the diode bridge goes to circuit ground. The plus side of the diode bridge comes down here and goes right into the power switch. The output of the power switch goes to 470 microfarad electrolytic to ground, and then that point feeds the switching voltage boost circuit. I think what this is doing here is it's a signal detector. If it detects either polarity of signal coming in here, in other words, if there's any kind of power supply hooked up here, then it passes down here, and this is the 9-volt battery coming in. Its minus side is going to ground. Its plus side, well, it seems like this has got to be a series pass transistor, which in turn goes through a diode and then to the same place as the output of the bridge up here. So this would be where the battery supply or the battery supply or the auxiliary supply come together to the power switch. Because this point is fed by two diodes, that would prevent backflow, and then this side has a diode here to prevent backflow going the other direction. Now, as I identified it, this transistor here should be an NPN, but I'm not sure that's correct. That may be a misidentification. Let's look at what I have here. If you have a signal here that's positive, then it gets through these diodes, it comes down here and it turns on this transistor, which goes between the plus of the battery and circuit ground. Turning that transistor on would essentially bring the collector down to circuit ground, and otherwise it's pulled up through these resistors, but when it gets pulled down, that essentially makes the base of this PNP transistor grounded, which is what it takes to turn on a PNP transistor. And then this one would feed and develop a voltage drop across this resistor to ground. So you'd now have a voltage here, and that would turn on an NPN transistor, which this is, but it's connected backwards as far as I could tell. And I know you can use NPNs backwards and treat them as sort of an analog switch. Maybe that's what they're doing here, or maybe I've transcribed the circuit incorrectly. But I think what the upshot of this is, let's pretend like this is actually a PNP transistor. So this point going high would turn this one off, and it would not be able to pass it. In other words, what if instead of the NPN I have drawn in here, I remove that emitter arrow and treat this as a collector. Oops, no, I should go the other way. This is still the emitter, but now it's a PNP. So if this point goes high, then that turns the PNP off. It will not pass battery power through the diode into the power switch. That makes more sense to me. I think what that would do is tell the battery circuit, hey, there's a better power supply up here, you can shut off. But maybe I've misinterpreted. Some of the values and connections are really hard to trace out, so this may actually be doing something a little bit different from what I have. I think suffice it to say that there is some circuitry here so that you don't deplete the battery if you've got power coming in from the auxiliary, and that either the battery or the aux through diode coupling can feed into the power switch, and from there feed the switching voltage boost circuit. As I thought earlier, this collection of parts here is some sort of a switching boost circuit, a voltage boost circuit. It has to take a variable amount of voltage coming from the battery or from the wide voltage span, 7.5 to 12 volts coming in from the auxiliary. It has to take that variable range of voltage and convert it to a more or less consistent 46 to 48 volts DC. Because of the presence of some really small inductors there and that 5-pin surface mount component, as near as I could tell it, that is identified as a SH1B. And one of the things with surface mount parts is for any given designation like that on the part, there's often quite a wide range of different components which that designation might refer to. But looking it up online, it seemed like this was probably a Texas Instruments LMR 62014, which is in fact a 5-terminal simple switcher. I think it might be inherited from the National Semiconductor line that became part of Texas Instruments. I think they pioneered the simple switchers. And it certainly has the 5-pin surface mount package, and somewhere on this data sheet, but I didn't print it out, it does reference the SH1B as one of the surface or the component markings. So I'm going to say that's what that is. And essentially what you have on there is a voltage input. This would be your variable voltage in this case, coming from the battery or the auxiliary input after the power switch. And you'd have circuit ground connected. You'd have a switching output, and you'd have a feedback input, and then you'd have a shutdown, which you can use to disable the operation of the chip. But essentially, if you connect your variable or unregulated voltage from here to here, depending on how you configure the circuit, this can convert the voltage to something else. So this shows a typical circuit. It may or may not match this very closely. There's a lot of different ways to implement these circuits, but this is sort of like a bare bones circuit with you got your, say for example, a 5-volt input, and then you've got a resistor pulling up the shutdown, which if it goes low it shuts it down, and there's a filter capacitor to ground, and besides powering the chip, the input voltage goes into a inductor. This suggests a 10 microhenry. These parts are marked 100, which might mean 100 microhenries, or it might mean something else. And so voltage is applied to that. The other side is connected to the switch pin on the IC, which I believe just has a transistor going from there to ground. So it can pull this low and then release it, and there's a Schottky diode here, and just doing that can produce a stepped up voltage. And then you take the output and you run it from the output of the Schottky diode, you have a voltage divider comprised of a couple of resistors back to circuit ground and a filter capacitor across that. Now this is a mistake here, there's no pin here, but you'd get a voltage here dependent upon the output voltage, and that goes to the feedback pin. Depending on what that voltage is, it changes the duty cycle of the constant frequency switching output here. And by doing that, you take a bigger or smaller slice of voltage or power that's transferred through this thing, and that ends up developing the desired voltage out here. So it's a voltage regulator as well as a step-up circuit. Now, the specifications say this can only do 20 volts maximum output, but we need 46 to 48 volts over here. And I only see that one IC here, but I do see two inductors. And without tracing this out, which would give me a headache and make my eyes go on strike, I'm guessing what they're doing is something a little tricky here. They may be turning this into a dual stage booster, where it boosts it once, then boosts it again. There's an extra transistor down here. I don't know if that has anything to do with it. I don't see any other active components up here. I do see just, well, there's another inductor here actually. It's marked as L4, L3, L1. There might even be another inductor in here that I can't spot right off, but oh yeah, L2, that's down here. So again, I don't know how they're working this circuit with this one IC to do it, but it's obviously more complicated than just this basic configuration. However, as I've already demonstrated, it does work and it gets the voltage up to there. Now, in several places, I saw something in reference to a CMOS circuit that provides the phantom power. I don't see anything about this that would suggest to me a CMOS circuit, so I'm not sure what the heck that's supposed to mean. Probably somebody in marketing screwed up. Now, I took this apart very carefully, and I noticed something when I did so. This otherwise unsecured battery insulator made out of cardboard seems kind of chintzy. I think they could have had like a molded plastic part or something. You know, it would serve to keep the battery in place, and the battery would take up the space of that, but there's really nothing that I can see to keep it from sliding out the back. You know, what's keeping it from banging into those components? I don't care for that at all. I almost wonder if they left out a part. I was looking very carefully to make sure there was no parts that fell out of it, and took it apart very slowly. But I'm kind of considering giving them a call and say, hey, you know, I've noticed that the battery seems to be able to slam all the way back in there. Isn't there supposed to be something restricting it? And if they say, no, that's just the way it is, then I'll maybe bodge something up to go into this space. Maybe another piece of foam or something that will sit in there and kind of block it from coming back further. And if they say, no, it should have a piece, I say, well, mine didn't have it. And see how that works out. Alright, I have this hooked up with my Fender Passport, whatever model it is, PD250 or whatever it may say on here somewhere. I've got a couple of Shure PG81s connected up to the inputs of the phantom power supply, and then just some short cables connecting those up to the mic inputs. So I'm gonna turn the power on.
And I'm going to just bring these up to a pretty low amplitude on the masters. And something like that, so I don't blow the neighborhood away. 1, 2, 3, 4. 1, 2, 3, 4. Try the other one. 1, 2, 3, 4. 1, 2, 3, 4. Testing, testing. 1, 2, 3, 4. Trying the other one. Seems to be working. I don't hear any hum or hiss or anything. The amp seems fine with it. As I expected, there really shouldn't be any issues.